Okay, I've started the recording. Let's start. So, good afternoon, everyone. This is fifth interactive session. Today is 24th August, and the time is 3 p.m. So, these interactive sessions for the NPTEL course Experimental Physics 1 happens every Saturday from 3 p.m. to 5 p.m. This course is being taken by Professor Amal Kumar Das from IIT Kharagpur, and I am Rinalini, PMRF Research Scholar, School of Physics, University of Hyderabad. So, in the last session, that is the fourth interactive session, we discussed about error analysis and did solved problems based on this topic. So, for reference chapter or reference book for this particular concept will be, one is this book titled An Introduction to Error Analysis. It is by John R. Taylor. This is a good book. Also, you can refer to NCERT class 11th physics books chapter 1 or 2. They also contain summarized problems and theory on basic error analysis. So both these sources are good for that. Okay, so let's have a quick recap of what we discussed last time. So now, after 3 weeks lectures, finally we have started discussing the particular experiments now. In last week we discussed the theory, the basic theory we should keep in mind when we are doing the experiment for determination of Young's modulus of a material. So last time we had discussed, under the theory we had discussed about what is elasticity and plasticity of a material, what is stress and strain in a material, and from the Hooke's law how we define elastic modulus for any given material, which is the ratio of stress applied to the strain produced in a material. So the ratio, the elastic modulus is given by the ratio of stress, to strain, where these modulus are also of different variety depending on what kind of stress was applied and what kind of strain response is produced in the material. For example, if the stress, that is the force, stress is force per unit area, right? So if the force applied to the material is producing change in length of material, then it will be tensile stress, and the strain produced will be tensile strain. And the ratio of this tensile stress to tensile strain is known as Young's modulus. Whereas if there is a material of volume V, and we are applying stress on it such that its volume is reducing, then this stress will be called volume stress and the strain will be called volume strain, and the ratio of this stress versus strain will be called bulk modulus. So these were the things that we discussed. We also did few problems based on it. Now moving forward to this week's, based on the things that the professor discussed this week. So this week we started the procedure, the experimental procedure of determining Young's modulus of a material. So Young's modulus, as we saw, it's a constant. It is defined as mechanical property of a material to withstand the compression or elongation, basically any kind of change in its length with respect to its original length. This is a constant for any particular material. So like if something is made up of any copper material, so the Young modulus for that will be same, doesn't matter if that material is in form of a wire or form of a cube or form of a sphere. So Young modulus is a constant which is the property of a material. Like we know, for different material there is electrical conductivity we define, right? Resistivity we define, which is constant for any kind of particular material at constant temperature. The similar way, Young's modulus is a constant which is different for different materials, and it is independent of size and shape. So as I mentioned, that doesn't matter if that particular material is in form of sphere or wire or any other shape, the Young's modulus, this constant, will be same for that material. Now there are different methods, like two methods that we'll mention, which are used to determine Young's modulus for a material in lab. So one method is flexure method, where the material for which we want to find out the Young's modulus, that material is taken in form of bar or beam. As you can see here, this is a bar or beam, we can call it, right? So in flexure method, we take the material in form of a bar or beam. Whereas there is another method called Searle's method, where this material is taken in form of a wire. So this is a bundle of wire, but as you can see, for our experiment, we can take the required amount of wire, a straight wire out of this bundle, and we can do our experiment on that to determine the Young's modulus for that particular wire material. So let's move to the flexure method and let's see how it is performed and what is the formula with using which we find out the Young's modulus constant. So for flexure method, as we mentioned, that the material is taken in form of bar or beam, like this, something like this. What we have to keep in mind is, when we take such kind of bar or beam, we should keep in mind that the length of the, let me define here. So this is a bar or a beam, it's a cuboid kind of, it is a cuboid, but what we have to keep in mind is, here this is the length, right? This is the length, this is the breadth or width, you can call, we denote it by small b, and this is the depth or the thickness of this bar. So what we have to keep in mind is, when we want to take suitable bar or beam for this experiment, is the length should be greater, much greater than the breadth or the width, which should be much greater than the depth or the thickness. So let me just write this clearly. So the length of the bar should be greater than the width, should be greater than the thickness or depth, we can call it anything, so thickness or depth, width or breadth. So this is the condition we should keep in mind for the material. Now how do we perform this experiment is, so these two are called knife edge. These are called knife edge. Knife edge is basically something like one end of a knife, right? One end of knife is sharp, so it is something pointy, and below it can be anything like flat, so that we can keep it in a surface, but pointy at the top. Yeah, so something like this is called knife edge in experimental labs. And so we have, as you can see, we have two knife edge stands, on top of which we are keeping, this is our bar or beam. This bar or beam is made up of the material for which we want to find out the Young's modulus. Okay, so this is that bar we have kept, and the length here that we consider is the length between this knife edge, not this whole length, but the length between this one end of knife edge, the another end of knife edge. So the length that we are talking about here, when we calculate the Young's modulus, the length we consider is between this and this. We can measure it using any meter scale and find out what is the length of this much, this length of the bar. Now at the center of the bar, we start putting the weight, and So initially it will be flat, right? We'll keep two sharp on this knife edges, we'll keep a bar, and this is the this will be the L, and at the center of this bar we'll start hanging our different weights. They will have some different mass, and there will be acceleration due to gravity acting on these weights, so we can call the weight will be the mass times gravity. Okay, so when we'll hang these different weights, it will bend, right? Because of the weight, it will not remain straight, but it will bend. So it will start bending, and this deviation that we see, we'll measure this deviation using this microscope called traveling microscope. So it's called traveling microscope because it can move left, right, it can move up and down depending on our requirement, and there will be some, like we had seen in vernier scales and screw gauge, so there will be some scaling on this particular object that we have hung here, and based on that reading, so we'll take initially some reading, and after hanging there will be some depression here or some this bending, so the mark will move down, and then again we'll move our microscope down, and then accordingly take the reading. So this is the basic experiment that has to be done, and what we'll keep on doing is we'll keep on changing the masses and corresponding what is the depression in, what is the change in, or what is the depression here in the material, that we'll keep on noting down. So okay, so we know that the Young's modulus, we know that it is defined as stress upon strain, which is, okay, let me write, it is stress upon strain. This is the basic, we know the ratio of this. We also know we can write it as stress is force per unit area, and strain is, for Young's modulus, change in length to original length. This is how it is defined. But for this particular shape of material, here I'll just give you the direct formula, we don't need to derive it or anything. So for a bar or a beam, the Young's modulus is defined as GL divided by 4BB³ and M by L. Okay, so as we saw here, the force, this will depend on the mass, and the acceleration due to gravity, this is area of cross section, that will also depend on volume and length and these things. So the final formula, the working formula that we find is like this. So this is, we can just take it that this is the working formula for a bar or beam to find out the Young's modulus. Now so for any, if I'm taking any material, the length is same for it, the breadth of the material is same, the depth we have measured, it will stay same. What will keep on changing is the different mass. So every time I'll keep on changing the mass here, keep on adding, like initially if I started with say 50 gram, later I'll make it 100 gram, then 150 gram. So the mass is changing, and corresponding the depression here will change, which is represented by small l here, the change in the depression. So another way to find out this is, if we plot it like this, this is load, or you can say mass. Whatever is the mass, accordingly there will be mg, right, the load, and there will be depression. Which is represented by small l here. So for some, like say for m and l, for some mass 5 say 50 gram, it moves to some 2 centimeter, and for 100 gram it moves to 4 centimeter, like this. So when we'll plot that for, say this is 25 gram, this is 50, this is 100 gram, and then correspondingly there is 2 or 4 centimeter depression. So this, so we'll plot one here, one here, and corresponding we'll plot these data points, and we'll see that there will be linear relation, right? Because all these values are constant for a material, so it's basically constant. What is changing when I'm changing the mass is this change in depression. So it's, you can see it's like a linear relation. So when we'll plot this graph, we'll get this kind of straight line, and the slope of this, will be some mass, this is 50, right? So this is basically delta m, this is basically delta l, and the slope of graph will be delta, yeah, delta l by delta m. So this is also load depression, this is called load depression graph. Okay, so let's do a question based on this. So there are two wires are elongated. Okay, so you understand that this is one way of calculating, or we know all this, and then m by l or delta m by delta l, the slope whatever we'll get, we'll multiply, and this we get Young's. So this is how we do it for experiment. While doing experimentally, as the professor had told, that we need to take care in mind that we need to repeat the measurements. So we'll do, we can repeat it with different length. Like for say, first I did it with say 70 centimeter of length of the bar. Next time I'll do it with 75 centimeter of length or 80 centimeter, depending on it. I mean, the, as we had discussed in earlier sessions, that we should repeat experiments several times and then take its average, so that we can get the measured value as close as possible, as error free as possible. And also when we calculate, we should keep in mind the concept of significant figures, the concept of error analysis that we discussed last time. So keeping in mind all these concepts, we will calculate the final value. So this is what we have to keep in mind while carrying out the experiment. Now, because we have to do the assignments, so assignments mostly contain the theory part, so we'll do some uh, these are assignment problems from previous years, and also some more questions that I have added. So let's do this first question, which is two wires A and B are elongated by same force. So I have wire A and wire B. Wire A and wire B. The ratio of initial length of A and B is 2:1. So say length of wire A, I call it LA. For this I'll call it LB, and it's given two wires are elongated by same force. Force is applied on wire A, I'm calling it FA. Force applied on wire B, let's call it FB, and it's given that same force is applied on both. Okay, the ratio of initial length of A and B is 2:1. It is given that ratio of LA to LB is 2:1. The radii of A and B is in the ratio of 2:1. Again, the radius of wire A, let's call it RA, radius of wire B, let's call it RB, and it is given again in the problem itself that radius of A wire to radius of B wire is 2:1. So in length was also in 2:1 ratio, radius is also in 2:1 ratio. The elongation is in the ratio of 1:2. So the wires are this is the original length. Okay, when the wire is being pulled by applying some force, then say some uh, small L changes happening in the wires. So the change in wire A, let's call it LA, small LA, and in B wire, the change, let's call it LB. And it's given the elongation is the change, right? The elongation is the change when the force is applied. So the ratio of this is also given, LA to LB is 1:2. The Young's modulus of A and B is in what ratio? Okay, again recalling that Young's modulus is force per unit area divided by the change. Here we are calling the change by small l, we are denoting the change by small l, and this is the original length. So simplifying, it will become F A capital L by small l. The Young's modulus A and B. So Young's modulus of A will be FA LA divided by area of wire A and change in this. Young's modulus for wire B, FB LB divided by AB is this. Now, as was given, the force is same. That means FA is equal to FB. So when I will take this ratio, which is what we have been asked in the question, then it will become FA LA divided by this, right? Means AB LB divided by AA LA FB LB. So as given that the force is same, that means this is same, we can cancel it. Now okay, little bit let me arrange it properly. LA, I'll keep the lengths together because we know these ratios, so I'm just writing it in a different manner. AB divided by AA and the change LA. Okay, now what we know is LA to LB is 2/1. So 2/1 times AA. Okay, so area, we know area for wire is what? It's like I mean area, force per unit area. So it's pi r square, right? Because it's a circular end. So pi r square. So substituting this, it will become pi, and area of B wire means radius of B wire square divided by pi radius of A square into LB is to LA. Now LA is to LB is 1/2. That means LB is to LA will be reciprocal. That is inverse of this. That is 2:1. This pi will also cancel. This 2/1 multiplied by 2/1 will be 4/1, right? And this RB is to RA. Now RA is to RB is 2/1. That means RB divided by RA will be 1 by 2. That is what it is, 1 by 2 and square. So we'll get 4 by 1 multiplied by 1 by 4. That means 1 by 1. So the correct answer here is, the correct answer is 1 by 1. Okay. Moving on to another question. The following graph shows the load versus elongation. This is load on x-axis. Here we are showing load on x-axis and elongation in y-axis. So as we had discussed earlier, load elongation or load depression graph this is for 4 wires of same material and cross section. So what it has been given is the material is load versus elongation for 4 wires of same material. So we have taken 4 different wires, but they are made up of same material and their cross section, area cross section is also same. We have been asked which wire has longest length. So we again taking Young's modulus, the formula will be force upon area, and yeah, this is the change, or if you want we can change in length, we can denote like this. So this is the formula, and we know that Young, okay, let's rearrange this little bit, then I'll explain. So what we know, okay, delta L divided by L, delta L divided by L will be force upon area multiplied by area. Okay, so why I have written is like this, because we have been told that these 4 wires are made up of same material. That means Young modulus value for all the 4 wires is same, and let us call it Y. The cross section is same for all the wires, means their area is same, and okay, the following graph shows load versus elongation for 4 wires of same material and cross section. Now say for any point we have applied load, means so this force is what? This force is, we can call it mass times acceleration, right? Here this force is load. Load means whatever the material we have put, that 5 gram or 50 gram, and the acceleration due to gravity which is acting on it. This together will give us the force or the load. So for any particular value of load, say this, for any particular value of load, we can see that for wire D, this is constant. So any value, say, I mean whatever load L I have already used, let's call it W. For any particular load W1, the elongation is in D wire, let's call it L small d, and the same value of load is causing elongation, you can see, of LA. So we can see that for any particular value of load, we can clearly see here, right, that LD value is much smaller than LA value. Similarly, if you see where it's, I mean this particular value of x-axis, it's cutting these slope. So it's cutting the slope here, corresponding y value will be the elongation in B wire. Sorry, it will be the elongation caused in B wire. Similarly, the slope, it's intersecting here. If I'll take the corresponding y value here, it will be LC. So this particular load value is causing this much elongation for D wire and more elongation for C wire, more elongation for B, and the maximum elongation in A. So this is constant because it's same for all the material, and if I'm keeping the force also same, then all this is a constant, and what we see is delta L1 upon L, sorry, for A wire it is this, for B wire it will be this, for C wire, D wire. So this is all constant, means what we are seeing, these values are constant, right? That F divided by AY. And this is a constant, means these all are constant. So what this means is this change in any wire, any of these four wire, whatever it is, the change in the wire is proportional to the length of the wire, original length of the wire. The same is the case for B wire also, and the same is the case for C wire and D wire also. So this is one relation that we understand. Now as we saw from here that for any one particular value, the change, these are all these deltas, the change, okay, it depends on how we want to represent, with delta or without delta. So we see that for particular value of weight, the maximum change or maximum elongation happens in wire A, and since the change is proportional to the original length, thus we can clearly say, we have been asked which one is of longest length, then we see that the maximum change is happening in wire A. That means the maximum length is also of wire A. So the wire A has the longest length here. I hope you understood this. This is important to understand because there were many questions based on this kind of problem in this year's assignment as well. Okay. So yeah, there was one more experiment called determination of spring constant of a material. So earlier one was determination of Young's modulus of the material. Now this one is determination of spring constant of a material. So according to Hooke's law, the force required to compress or extend a spring is directly proportional to the distance it is stretched. So like this is, I have a helical spring, the usual spring that you know, and there is, there is no mass attached to it, then it is in some equilibrium position, and when I attach some mass to it, then this was its original position. Now it will move this by this, again the depression, elongation, anything you can call it, but its length will change now by some x, or you can call it L or delta L. It all is about the denotation. You can denote it by anything, it's okay. So original length was say L, now it becomes L plus delta L. When I am putting a force, the force here it is in the form of what? mg. So when I am applying force here, there is some extension, and from Hooke's law tells us that this force is directly proportional to the displacement, and the direction of restoring force is opposite. Actually, when we apply force on any kind of material, we know there is one restoring force, right? The system wants to bring itself to the equilibrium position. So there is one force generated inside this material which we call as restoring force. So that restoring force is in the opposite direction. I am applying force in this direction, right, the gravitational direction here, and there is restoring force produced in the material in opposite direction. So to represent this opposite direction thing, we put a negative sign, and removing this proportionality constant, we put a constant value here, equality, and this k is called the spring constant. It is also property of the material, and we can also define it as restoring force per unit elongation. That is, K is, this is again for direction, it doesn't change anything in magnitude, but spring constant is defined as restoring force per unit elongation. So this is what is spring constant. Now to carry out, to determine spring constant for a given helical spring in lab, if we carry out the static method experiment, here what we do is we hang a spring from a support on some roof or some place, and then we'll, like the way we did the experiment for determining Young's modulus, we were keep on adding the weight and there was change, there was depression, right, the change in the beam depression. The same way for the spring, we'll keep on adding or we'll keep on changing the mass, and there will be elongation in this spring. So in detail you can refer the lectures. The professor has explained it very nicely. He has shown the while doing the experiments as well. Here we will mainly focus on the theory and the problems based on this. So I'm not going into much detail, but this is how a typical setup looks. There is a scale which helps us to know the value of displacement, and again when we'll plot this load versus extension graph, it will be a straight line and the slope will give us the spring constant, right? Because F is equal to minus kx. So this is x here, this is the force, right? The mass times gravity, if we'll do, that will be our force. So the slope will, from the slope we'll get the spring constant value. So this is what the basic experiment is about. Now let's do some questions based on this as well. So okay. Okay. So sorry, there was power cut. Actually, there is power fluctuation today. So, but okay. Again, for time being, we are connected. We have internet back. So let's start from where we stopped. With discussing this, we discussed the spring constant experiment, how to determine spring constant. Now let's do some questions based on this. So first question is, a spring with load 5 kg is stretched by 40 centimeter. Determine its spring constant. So we know that the force here applied is, we know force will be this mass times the acceleration due to gravity. That means this 5 kg times, if we take 10, we know that acceleration due to gravity is 9.8 meter per second square, but here for ease we can take 10 meter per second square, and so this will become 50 Newton, right? Kg meter per second square, or Newton we can call it. Force is stretched by 40 centimeter, means that change in length or the elongation is 40 centimeter. Now we should keep all the units same, so changing it into meter, so 40 centimeter in meters, it will be 10 to the power minus 2, right? Yeah, that means 0.4 meters. So spring constant, now we know K is F by this elongation. On delta L or X we can call it anything. There is a negative sign also, but for magnitude we don't need it. We know it's just to denote the opposite direction. So the spring constant can be found out like this, that is 50 Newton divided by the elongation, that is 0.4 meter. 50 divided by 0.4, just calculate quickly. 50 divided by 0.4, this will be 125 Newton per meter. Just let me check if the video and everything is working fine. Yeah, audio. Okay. And the recording is also fine. Okay. Yeah. Moving on to the next question. This question says that 3500 Newton force is applied to a spring that has a spring constant of 14,000 Newton per meter. Calculate how far from equilibrium the spring will be displaced. So we know that equilibrium is like this is the spring, and without any weight, without hanging any weight, it is at some this L length. This is the equilibrium. When I hang the weight here, it will get elongated. Okay, it will become something like this. This is some weight, and this is the weight, and there is some elongation rate. So this was equilibrium position. This was equilibrium position, and this is now the new scenario where it's elongated. So the force applied is 3500 Newton force is applied to a spring. Spring constant is given to be 14 Newton per meter. Calculate how far from equilibrium the spring will be displaced. That means we have been asked to calculate this x, or whatever you want to call it, delta L or something. So we know F is minus kx. So that means x will be F by k, right? So this x will be F, which is 3500 Newton, divided by this k, which is 14,000 Newton per meter. So the final thing we'll get is divided by 14, 0.25 meters. So the displacement is 0.25 meters. Moving on to the next question. No. So okay. So now it's about the third experiment. Before that, let me check if the internet is fine or not. Again, it's disconnected. Let me just connect it. Okay. I'm sorry, today this internet outage and power fluctuation is keep on happening. Let's continue. So the another experiment that we started talking about is determination of moment of inertia of a flywheel. So in today's session, because last week's lecture also, the professor covered the theory behind this, and another week we'll be talking about the procedure of doing this experiment. So for this interactive session, we'll cover the theory of moment of inertia. So let's start by understanding that how we come to talk about moment of inertia of any object. So when we talk about linear motion of any object, say there is some spherical object and there is force applied on it, because of which it moves certain distance. Okay, so in for this linear motion, the equation of motion for this equation of motion will be this particular situation. Equation of motion will be force, right? Force is equal to mass. Let's say mass of this object is m, and acceleration. Here the acceleration will be the d2x by dt square, double derivative of this displacement with respect to time. This will be the force. Now for same object, if it undergoes rotational motion with respect to an axis, for example it's circular, it's following this circular path, the same object, let's consider, and here after displacement it had reached to another position, right? The same way here it's starting, this is the same object of mass m, and it's moving in this circular path. This the axis of this the circular path, let's consider here is the axis, and around this axis it's rotating. Initially it was at this position, it is at some distance r from this axis of rotation. Initial position is this, after a certain time it reaches another position, this. So this angular displacement, this distance with the angular displacement, let's call it theta. So what's happening is we are applying a rotational force on this object, and because of which it's rotating around this axis. That rotational force will be called torque, represented by tau. It's called torque, and the equation of motion for this condition, equation of motion will be this. The rotational force is called torque, and it's given by I into, like here also what it was, mass times acceleration. This acceleration was linear acceleration, right? For this rotational motion, the torque is given by moment of inertia times angular acceleration. The angular acceleration will be double derivative of this angular displacement, and if we compare equation 1 and equation 2, we see that this is the linear force, this is rotational force which is called torque, this is angular acceleration. In linear motion it corresponds to linear acceleration, and this I corresponds to this mass. So in rotational motion, moment of inertia basically is equivalent of mass in linear motion. So it's equivalence of mass. So this is what we understand from this comparison. Now further, so let's define what is moment of inertia. To put it in simple terms, moment of inertia can be described as a quantity that decides the amount of torque needed for a specific angular acceleration in a rotational axis. What it wants to say is that we know torque is this I times alpha, right? So I decides the amount of torque required to produce this much angular acceleration. Moment of inertia is also, for any object, it's given by the formula sum of mass product of mass times r square, where r is the distance from the axis of rotation. We'll see these things in detail little later now. Moment of inertia is also known as angular mass or rotational inertia, and SI unit is kg meter square. The moment of inertia depends on following factors. It depends on the density of the material, shape and size of the body, and axis of rotation. So like if there is this is the axis of rotation, object is here, this is r, this is m, then the moment of inertia for this object corresponding to this axis of rotation. Keep in mind that moment of inertia depends on axis of rotation. So if we consider the axis of rotation here, I mean this corresponding to this axis of axis, if we calculate the moment of inertia for this object, the basic this is it will be sum of mass, here only one mass is there, and then r square. Okay, if I'll take some other axis, then it will be some other value, like if we'll again see these things a little later. Okay, just to do a quick problem based on this. A constant torque is applied to a wheel, and as a result an angular acceleration of 25 radian per second square is produced in it. So torque is being applied, because of which angular acceleration alpha, which is given 25 radian per second square, is produced. Moment of inertia of wheel about the axis of rotation. So there is a wheel, okay, this is a wheel, axis of rotation is perpendicular to the plane of the wheel, and about this the moment of inertia is calculated to be 2000 kg meter square. Find the torque. Now we know torque is given by I times alpha. I is 2000, alpha is 25. So the final value will be, and wait, this is kg meter square radian per second square, kg meter, yeah, kg, yeah, this we can write as Newton. So it will be finally Newton meter, and this will be 25 times 2 is 50, and there are zeros. This means 50,000 Newton meter. We can put dash, we can don't put, this is the correct answer. Okay, again just let me check the internet, I'm sorry. Yeah. Moving on to the next question. The question is, 4 particles each of mass m are kept at 4 corners of a square of edge A. Find the moment of inertia of the system about a line perpendicular to the plane of square and passing through the center of square. So let's make the figure accordingly first to understand what the question is asking and what we have to find out. So it says 4 particles each of mass m are kept at 4 corners of a square. So let's make a square, and the edges are of length A. All these edges are of length A because it's a square, and 4 particles of mass m are kept at each corner. 4 particles, they are all of same masses m, they are kept at these corners of this square setup. Find the moment of inertia of the system about a line perpendicular to the plane of square. So this is 2D here, so I mean don't get confused, but this line that I am making, this is not parallel. This line is, this line axis that I am making, it's perpendicular to the plane of square, and we have to find out the moment of inertia. We have to calculate the moment of inertia corresponding to this axis. This axis is perpendicular to the plane of this square setup and passing through the center of this square. So as we had seen that moment of inertia is taken as sum of all the masses, right? This is like corresponding to first particle, its mass and its distance from the axis, and then so basically, okay, let me expand this. What it means is that m1 r1 square plus, because we have four particles here, m2 r2 square plus m3 r3 square plus m4 r4 square. We have 4 materials, so the summation will be for this 4 particles. So this is what it means. And okay, so mass is same, which is m, but we need to find out the distance of these particles from this center. So what we need to find out is this. And we know, since this is a square setup, that means these diagonals, these are actually diagonals here, and they are perpendicularly bisecting. So we know this property that for any square, diagonals of square are perpendicularly bisecting each other. That means this thing is half of the total. So okay, if I want to find out how much is this, like let's call this A, let's call this B, and let's call this C, and I'm making this triangle again here for keeping it little clear, because this I know, this is A, this is A. I want to find out, this is the center, right? This same center, let's call it O. Okay, I want to find out this this, let's call it R, this distance. I want to find out this distance, this much. So considering this whole length, let's call it L. Okay, and we know it's a square, means this is 90 degree, right? It's a square means all angles inside are 90 degree. So from Pythagorean theorem we can find out that this L square will be A square plus A square. That means this length L is 2A square root, right? That means root 2 and A. And now R is what? R is L by 2. That means root 2A by 2, which will mean it's A by root 2. That means, so all these particles are at same distance, right? All these are R, and the value of R is A by root 2, and all these masses are also same. So all the masses are m and all the distance R is A by 2. That means I can just make it 4 times instead of this doing plus, 4 times, and mass is m and R is A by root 2, and taking square of this, I'll get what, 4 times m square of this A square, and root 2 square means 2. This will be, so the 2ma square. So our answer, that is the moment of inertia of this particular system corresponding to this axis, will be 2ma square. Moving on to the other. Okay, so in similar way there are different kind of bodies for which actually these kind of things we have already studied in, I think, standard class 11th or class 12th. We have done moment of inertia and these how to calculate for different kind of bodies, like for a cylinder, for a disc, for a ring, for solid sphere, hollow sphere, rod, and also like in this particular row it's all through the what the center of rotation, I mean the axis of rotation is the passing through perpendicular to the object, passing through its center. But we know there are different theorems using which we can find out the moment of inertia for these different shape or different size objects. And okay, so since we said that the moment of inertia depends on the size and shape of the body, here we were saying this, right? Moment of inertia depends on density of the material. Density, because it depends, the formula depends on mass, right? And at what distance it is from the axis. So that's why it depends on the density of the material, that how the mass is distributed in the material. It depends on the shape and size and the axis of rotation. So for calculating moment of inertia for these I have just given you directly. We don't need to derive it again and again. But we know that we have two theorems based on which we can find out the moment of inertia for these kind of objects in along different axes, right? Like these are parallel axis theorem and perpendicular axis theorem. So let's do quick review of what these theorems tell us. So first, let's talk about parallel axis theorem. So what parallel axis theorem tells us is that, like, for in this figure we can see that this is okay, let me read it out. The moment of inertia of an object about an axis through its center of mass is the minimum moment of inertia for an axis in that direction in space. The moment of inertia about an axis parallel to that center of mass axis is given by the moment of inertia through the center of mass plus product of the mass and the distance between these two axes. So say this is, I have a shape, I have some material in this particular shape, and perpendicular to this shape I am drawing an axis, and that axis is passing through center of mass. Center of mass is basically where we can imagine that whole mass of the body, we can say that whole mass of the body is situated there, and if we balance that particular point, the whole material could be balanced. So that's why we call the whole mass, we can imagine it's situated at that point. So that point in the material, it can be inside or outside also, depending on for some ring we can also say that center is center of mass, where actually the ring is, mass of the ring is not there, but I mean that's how it's defined. So depending on the position of the material, here let's say this point is the center of mass, and which the axis passing through the center of mass and perpendicular to the plane of this object is corresponding to this axis, we will get our moment of inertia, ICM I am calling it. If I want to find out moment of inertia for the same object corresponding to this axis. Now this axis is also perpendicular, but it is not passing through the center of mass, but it is at some distance d from the center of mass. Then how can I calculate this? So the center of mass corresponding to this axis is ICM plus mass of this object, which is m, multiplied by this distance d square will give me this I. This I is corresponding to this axis. This is what we mean by parallel axis theorem. Now what is meant by perpendicular axis theorem? So for any plane body, the moment of inertia about any of its axes which are perpendicular to the plane, here the perpendicular to the plane is this IA, so which is perpendicular to the plane, is equal to the sum of moment of inertia about any two perpendicular axes in plane of body. The perpendicular axis in the plane of the body is IB and IC here, right? I mean the axes are this blue one and this green one. The perpendicular axis is this pink, magenta, you can call it, some color, this pink color. This is perpendicular, this axis is perpendicular to the object, and this blue and green axes are in the plane of this object, but they are perpendicular to each other. So what this perpendicular axis theorem says is that moment of inertia corresponding to this pink axis, which is perpendicular to the plane of the object, will be sum of moment of inertia corresponding to this blue and green axis. So this is what the statement means. Okay, so let's try doing some questions based on our understanding of these axis theorems, and we'll take help from this directly given moment of inertia values also. Let's see how we can put them to use. So the question is, three rods each of mass m and length L are joined together to form an equilateral triangle shown in figure. Triangle as shown in figure. Find the moment of inertia of the system about an axis passing through its center of mass. This is center of mass and perpendicular to the plane of triangle. So yeah, as I was mentioning earlier, right, center of mass, we imagine where we can call that whole mass of the object is situated, and it can be balanced by balancing that particular position. Here we see that this is, this is a setup made by a rod. One rod is in this position, one rod is in this position, third rod is in this position. So basically the mass is all at this circumference or at the ends. There is no mass inside, but still the center of mass will be, center of mass for this particular setup will be here. So yeah, it can be in this kind of place also. Anyways, so moving on to our question. Three rods of mass m and length l. They are all of length l and mass m. Form equilateral triangle. The sides are same, the length are same, that means they are equilateral triangle. And also we know that if they are equilateral triangle, that means all these angles are same and all these angles are 60 degree, right? Because the total inside a triangle should make 180 degree. So there are three angles, means each is 60 degree. Find the moment of inertia of the system about an axis passing through its center of mass and perpendicular to the plane of triangle. So basically, I don't know how to draw. Okay, let me draw it like this. No, what I want to say is it's not parallel. It's not parallel. What I want to show is, okay, sorry, pen, yeah. If I want to draw, okay, I'll clarify this axis I'm drawing, but it's not in the plane of the triangle, okay? This is in the, this is perpendicular, because it's, I'm not able to draw 3D here, but just keep in mind, this axis that we are talking about is perpendicular to the plane of this triangle. So we need to find out the moment of inertia corresponding to the axis passing through center of mass. So again we need to find out what is the distance between this rod and the center of mass. So we need to find out this length, we need to find out. Okay, so one thing, what for a particular rod, okay, for a rod, and if the axis is passing through center of mass of a rod, then what is the moment of inertia? I think it's 1 by 12 m l square, where l is the length of this rod. Sorry, l is small here, so we'll take small l, mass, and 1 by 12. Let's quickly see from here. Yeah, so when rod and its center of mass is perpendicular, the axis is passing through center of mass and is perpendicular to the length of rod, then moment of inertia is 1 by 12 ml square. So we'll start from here. This is the rod, okay, of length L, mass m, and the moment of inertia for this will be this. Now, but we see that here we need to find out the moment of inertia where the axis is not passing through the rod but at some distance, and that distance, it's the same here, right? It is at same distance from all three rods. We need to find out this distance, let's call it x. We need to find out this distance x, and then it will be like the center of axis is somewhere here and the distance between this will be given by x. And we know that the final that we want to find out from parallel axis theorem, right, we know that it will be this I plus mass times this distance. It means this x square. From parallel axis theorem we know that if we want to find out at some parallel distance where the axis is parallel to the axis passing through center of mass, then this is the formula. But what is this x? So okay, let me make it a little big again. So what I need to find out, is actually this. Here is the center of mass. I want to find out this. I'm calling it x. I know this total length is L, that means this half is L by 2, and I know this whole angle is 60, means this half angle is 30, right? We know this will be tan 30 degree, that will be x divided by L by 2, right? Now tan 30 degree is 1 by root 3, tan 30 degree is 1 by root 3, so this will be 2x by L. That means x is what? X is L by 2 root 3. I hope this is correct. X is L by 2 root 3. So for one rod, first we'll find out for one rod, this will be, this I is 1 by 12 ml square. 1 by 12 ml square plus m, and this x is what? Here. Substituting that, L by 2 root 3 square. So this will be 1 by 12 ml square plus ml square. This will be 4 root 3, that means 3. 12. Oh, so it will be 1 by 12 plus 1 by 12. It will be 1 by 6 ml square. Now this is for one rod. We need to find out for 3 rods. So final for 3 rods corresponding to, this particular setup, it will be 3 times this I prime. That means 3 by 6 ml square. That means half ml square. So this is our answer. Okay. Again, moving on to the next question. If the moment of inertia of a body along a perpendicular axis passing through its center of gravity is 50 kg. Okay, this is kg meter square. Okay, and the mass of the body is 30 kg. So moment of inertia of a body along a perpendicular axis passing through its center of gravity is 50 kg per meter. So moment of inertia is 50 kg meter square, and the mass of the body is 30 kg. What is the moment of inertia of the same body along another axis which is 50 centimeter away from the current axis and parallel to it? So directly from parallel axis theorem, we understand, because this was also corresponding to the perpendicular axis passing to the center of gravity. Now the new one is from parallel axis theorem. The new one will be this I plus this, and the distance between whatever will be the distance. So this was 50. Okay, mass is 30, and the distance between these two axes is 50 centimeter. 50 centimeter we'll convert in meter, means 50 times 10 to the power minus 2 meters, right? Yeah. So okay, this was in kg. This okay, so 50 plus this will be minus 2 kg. Oh, sorry. This has to be taken square. This distance has to be taken square. Yeah. This is not correct. 50 plus 30. Or I can use this bracket. This will be 2500 minus 4. This will be finally kg meter square, but what will be this? Let me calculate. This will be 2500 multiplied by 30, divided by 1.5 is 50. So the answer will be 57.5 kg meter square. I hope I did the conversions correct here, and the answer should be this. Moving on to the other one. So the question is, a tree has a breaking stress of, again this is Newton meter square. This is Newton meter square. Tree has a breaking stress of 4.5 times 10 to the power 5 Newton meter square. If the density of tree is 900 kg meter cube, the maximum height up to which it can grow is. Okay. Breaking stress it is, means what is the maximum it can grow before, because the tree has its own weight, right? So there is a limit up to which it can grow, otherwise its own weight will make it break. So that is called the breaking stress. So the tree is growing, and every time it's growing, its mass is also increasing. Because of that, we know there is mass, means there is acceleration due to gravity acting on it, and the total mg is the force. So as the tree is growing, there is force acting on it. With every increase in mass, the force is increasing, and there will be a limit after which it will collapse or it will break. So what is that? Force per unit area will be called the breaking stress. This force, okay, this breaking stress, is this force per unit area. Okay, this mg divided by area. Now we have been given the density of tree. We have been given the density, which we also denote by rho usually. We have been given the density, which is 900 kg. It should be per meter cube actually. Okay. And this also, sorry, this is not Newton meter square. I think this is Newton per meter square, or Newton, meter raised to the power -2, because it's stress, force per unit area. So let us begin it. This 900 kg per meter cube is the density. Now we have not been given the mass of the tree, but we have been given the density of the tree. So first thing we will do is to write mass in terms of density. Now we know that density for any material is given by mass divided by volume, right? Now mass and volume for this tree, we can consider this tree like a cylinder. Okay, if you consider it like a cylinder, the volume will be what? Area of cross section. It's like a cylinder, means area of cross section times the height will be the volume. So is some area of cross section, and the height, let's take height to be h, so that will give me the volume. Now from here I can write the mass in terms of density times area of cross section times height. Putting this value here, the force will become rho a h times g, maximum height up to which it can grow. Okay, so stress is mg by a. The breaking stress is given to be 4.5 times 10 to the power 5, and force per unit area, and we know force is rho a h g divided by area. So area gets cancelled. Density we have been given 900 This is in Newton, this is SI unit, this is SI unit, so everything is fine. Height we need to find out, and G, okay, again if we just assume it to be 10 meter per second square, then I need to find out H means this 4.5 times 10 to the power 5 divided by this 9,000. So approximately what I will get is 4.5. How do I do this? Wait, 4.5 divided by 9, and this 10 to the power 3 and 5, so it will be 10 to the power 2, right? 5 minus 3, 2. 4.5 divided by 9 will give me 0.5. Let me just confirm it once. 4.5 divided by 9 is 0.5, right? And then multiplied by this. This will be in meters. Height will be in meter. It means 0.5. Okay, 50 meters. So the tree can grow up to 50 meters before it breaks because of its own weight. So the correct answer is 50 meter. This is the correct answer among the options. Yeah. Okay, one more question. This is a solid sphere of mass 4 kg and radius √5 meter is rotated about an axis passing through its center. A sphere, solid sphere. This is a solid sphere. Mass is given 4 kg and radius is given to be √5 meter. This is radius. Rotated about an axis passing through its center. It's a sphere, so I mean there's only one axis through center. Not one, I mean there are infinitely many axes passing through center of mass, and they all are equivalent in the sense that moment of inertia will be same corresponding to these axes passing through its center. Now from this formula that we had, okay, for solid sphere moment of inertia will be 2 by 5 mr square. Okay, 2 by 5 mr square. We'll use it here. Just let me write in case we need it. 2 by 5 m whatever is the mass and r square. About an axis passing, find the radius of gyration of this axis. Okay, so radius of gyration is what? So moment of inertia in terms of radius of gyration is written like this, where this k is called the radius of gyration. So from this radius of gyration means I by m and root of I by m. Okay, I is, so I don't think I need this formula. Okay, yeah, we need to first calculate this I. So this I will be 2 by 5 and mass of the body is 4 kg and the radius is √5 meters and square will be 5 meters square. I mean the radius square will be 5 by 5 meters square. So when I calculate this, I'll get 8. Its moment of inertia is Newton, sorry, what I'm saying, kg meter square. So this is the moment of inertia for this solid sphere. Now radius of gyration will be this 8 divided by mass. Again the mass is 4 and then I have to take the root. So it will be √2 and so it's the unit is meter. So answer is √2. Okay. Now one more question. The moment of inertia of uniform circular disc about a diameter is I. Okay, so we have a disc now. It's not a ring, it's a disc, like this whole thing. If a disk about a diameter is I, its moment of inertia about an axis perpendicular to its plane and passing through a point on its rim will be. So basically the question is asking us to calculate this. It's asking us to calculate moment of inertia about an axis perpendicular to the plane of this disk, right? This axis is in perpendicular to the plane of this disk and passing through a point on its rim. So I mean this is the circumference, or you can call it the rim, and the axis is passing through this, and it's also perpendicular to the disk plane, and this is center of mass, right? This axis is passing through center of mass, which we have been told that moment of inertia of uniform circular disk about a diameter is I. We have been actually told this, that moment of inertia about diameter is I. Okay, so from the perpendicular axis theorem, we know that Iz is Ix plus Iy. If I call this as Iz, then this is some Ix maybe, and here perpendicularly there will be Iy. Okay, and since this this axis is same, this Ix Iy will be same, right? Because they are same axis, just 90-degree apart. So Ix is equal to Iy is equal to I. From this theorem we know that Iz will be Ix plus Iy. Ix is I, Iy is also I, that means 2 times I. This is the relation. Now we also know that for a circular disk where the axis is passing through its center of mass and it's perpendicular to the plane of the disk, the moment of inertia is actually half mr square. This is the formula, we don't need to derive, this is just we can memorize that the moment of inertia for a disk in this corresponding to this axis is half mr square. Now we need to find out corresponding to this, let's call it I prime. Okay, so moment of inertia corresponding to this axis will be half mr square plus, this is I'm writing from parallel axis theorem, now keep in mind that corresponding to this plus this times the distance. Now what will be the distance between these two? This is center, this is rim, so whatever is the radius of this disk, so it will be that only. So 1 plus half will be 3 by 2 mr square. From this actually we can see this is this Iz, which was, this Iz was what? Half mr square, right? This Iz was half mr square. Because the final answer we need to find in terms of the I value. So half mr square was 2I, that means 1 by 4 mr square is I. Okay, so that means multiplying 4 by 4 mr square, this is 3 by 2 times 4, and 1 by 4 mr square means I, right? So this will be 2, that means 6I. So the correct answer is this. Okay, so these were the questions for today's session. These were mostly based on the moment of inertia theory. In next class, even the lectures in the coming this week will be based on the moment of inertia, how to find the moment of inertia for a flywheel, They will discuss how to carry out the experimental procedure, and then the following week we'll be doing questions, solving questions based on that experiment and others. So basically in this interactive session we started from understanding, yeah, so in last class we had talked about these elastic modulator. So based on that we understood how to determine the Young's modulus through this experiment. We did questions based on this. Then we understood another experiment where we had to determine spring constant of a helical spring. We understood how the experiment is done and again did corresponding questions. And then this final third experiment, which uh, we did understood the theory and tried to solve questions based on the theory, where we will try to find out the moment of inertia making use of the parallel and perpendicular axis of theorems. So just like this is what was the summary of what we discussed in this interactive session, and let's end it for today. Yeah. Okay, I'll stop the recording now.